3I Atlas has dramatically increased in brightness as the most significant solar activity outburst in decades intensifies. Over the past few weeks, the sky has become the stage for two cosmic phenomena that have surprised even the most experienced astronomers. On one hand, the Sun is going through one of the most active moments of its cycle, releasing bursts of energy so powerful they can alter magnetic fields, communications, and even the space weather surrounding our planet. And on the other, an interstellar visitor named 3I Atlas has begun to shine with an unexpected intensity as it silently crosses the solar system. This is not a simple coincidence. Both events are occurring simultaneously, and observatories worldwide have doubled their surveillance. This increase in luminosity caught attention not only for its magnitude but for the exact moment it happened, just as solar flares reached their highest point in years. 3I Atlas, only the third interstellar object detected in history, now reflects a much greater amount of sunlight than the models predicted. No one expected such a drastic change, and the first measurements suggest its surface could be reacting to solar radiation in a way never before recorded. In a universe full of mysteries, this encounter between an interstellar visitor and an unleashed sun could offer crucial clues about how matter from other stellar systems behaves. Welcome to a new scientific analysis of the cosmos. Before we delve into the sudden brightness increase of 3I Atlas and its coincidence with the largest solar outburst in decades, you need to do three things immediately to activate the scientific community. First, give this video a like to boost this discovery to more observers. Second, subscribe and activate the bell to receive the next updates on the real-time tracking. And third, go down to the comments right now and write Cosmos to join the global registry of those following this historic event. Do it now. We continue. Today we will talk about the sudden brightness increase of 3I Atlas, a body traveling from beyond the known limits of the solar system, and how this phenomenon is happening at the same time as the largest outburst of solar activity observed in decades. Both events are being recorded by telescopes and space probes, including SOHO, the SDO, and the Parker Solar Probe, which observe the Sun and its magnetic behavior with millimeter precision. In the coming minutes, we will explore how the scientific community is closely tracking every change in the brightness of 3I Atlas, which hypotheses have been discarded, and what new questions arise from this cosmic coincidence. Unlike speculation or fiction, here we will speak exclusively of verifiable facts and observational data backed by space agencies and astronomical centers. Because in science, every flash has an explanation, although sometimes that explanation takes time to arrive. Prepare to discover how the Sun, in its maximum expression of energy, and an interstellar traveler shining like never before, are starring in an alignment that is already making history in modern astronomy. During the month when 3I Atlas began to shine with unexpected intensity, astronomical observatories around the world were already on alert for another reason. The Sun showed signs of a sudden increase in its magnetic activity. Both events, the intensification of the interstellar object's brightness and the resurgence of solar storms, coincided in the same period, creating an unprecedented situation in the modern records of astronomy. 3I Atlas was originally detected by the Atlas system, a set of automated telescopes designed to identify objects that could approach Earth dangerously. However, it soon became clear that this body did not belong to the solar system. Its hyperbolic trajectory, which does not bind it to the Sun's gravity, confirmed it was an interstellar visitor. The third of its kind ever observed, after Oumuamua, and 2I/Borisov. Its passage represents a unique opportunity to study materials formed in other stars and regions of space, beyond the limits of the solar neighborhood. As observations progressed, astronomers noticed a sudden change in its apparent luminosity. Photometric instruments showed a sustained increase of several magnitudes, a behavior impossible to ignore. The scientific community began compiling data from different wavelengths, visible, infrared, and ultraviolet. The first hypotheses focused on a process of outgassing similar to that of comets when they approached the Sun, although the exact composition of 3I Atlas remains under study. Simultaneously, the Sun was going through the most active phase of solar cycle 25, characterized by an increase in the number of sunspots and flares. Space observatories like the Solar Dynamics Observatory, SDO, and SOHO, recorded multiple Class X eruptions, the most energetic on the solar scale. These explosions released enormous amounts of ultraviolet radiation and X-rays, capable of temporarily altering Earth's ionosphere and provoking auroras visible at unusual latitudes. What caught the attention of many researchers was the temporal synchrony. While the Sun was releasing one of the most intense sequences of flares in recent decades, 3I Atlas was reflecting more light than normal. Although physics does not establish a direct causal connection between the two phenomena, the coincidence led to a coordinated effort among agencies like NASA, ESA, and the Institute of Astrophysics of the Canary Islands, which initiated simultaneous observation campaigns. The objective was to compare solar activity data with the reflectivity and surface temperature of the interstellar object. The preliminary results showed that the brightness increase of 3I Atlas coincided exactly with a temporary increase in solar flux at ultraviolet wavelengths. This suggests that the surface or the material enveloping the object could react sensitively to intense solar radiation, altering its capacity to reflect light. Are you still here? That means you are among the few who understand the magnitude of this event. If you have reached this point in the analysis, write "following" in the comments so we know you endured the cosmic journey. And if you want us to continue tracking 3I Atlas in real time, subscribe and activate the bell now. Nevertheless, scientists insist on the need for caution. A temporal correlation does not necessarily imply a physical link. The coincidence is intriguing, but it must be analyzed with rigor and reproducible evidence. Meanwhile, the Sun continued to show unpredictable behavior. Images from the Parker Solar Probe, the closest probe to our star, revealed enormous coronal mass ejections extending millions of kilometers into space. These eruptions released charged particles traveling at mind-boggling speeds exceeding 1,000 kilometers per second. When these particles reach Earth's magnetosphere, they generate geomagnetic storms that can interfere with satellites and electrical systems. This context of solar hyperactivity creates an ideal natural laboratory to study how radiation affects transiting bodies like 3I Atlas. For the first time, scientists can simultaneously observe an object from interstellar space and a sun in full energetic effervescence. Every photon, every variation in the visitor's light curve offers clues about the composition of materials formed around other stars. The tracking of 3I Atlas continues uninterrupted. Ground-based telescopes in Hawaii, Chile, and the Canary Islands record its position night after night, while space observatories capture spectroscopic data. Indications of volatile gas emissions have been detected, possibly composed of carbon and oxygen. The intensity of the brightness suggests that part of the surface material could be sublimating due to solar heat, creating a tenuous coma around the main nucleus, a phenomenon typical in bodies containing interstellar ice. However, this behavior does not invalidate its external origin. In fact, it confirms that interstellar matter can behave similarly to comets in the solar system, despite having been formed in completely different environments. Every measurement adds another piece to the puzzle of how matter is distributed and evolves in the galaxy. The scientific interest also lies in the possibility that during its brief passage, 3I Atlas might reveal chemical differences compared to local bodies. The obtained spectra show atomic lines that do not completely match the typical patterns of known comets, which reinforces the idea of a distant origin. Analyzing its brightness under the influence of extreme solar radiation will allow us to understand how organic and mineral compounds behave under non-equilibrium conditions. This scenario, a sun in its maximum energetic splendor and a visitor from another stellar system reacting to that radiation, constitutes a unique opportunity for modern astrophysics. Every day, scientists cross-reference data on temperature, density, and composition, seeking patterns that explain why the brightness of 3I Atlas increased just as the Sun reached its most active point. In the following sections, we will delve deeper into what this interstellar object truly represents, how it was discovered, and what sets it apart from the previous ones. What until recently was just a faint point in the sky has now become another key to understanding the dynamics of the universe. 3I Atlas is not a common comet nor a typical asteroid from the solar system. It is the third confirmed interstellar object in history, and its detection represents one of the greatest achievements of modern astronomy. Its name comes from the system that discovered it, the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of automated telescopes located primarily in Hawaii and designed to alert about potentially hazardous objects approaching Earth. The prefix 3I literally means third interstellar, in reference to its predecessors, 1I/Oumuamua, detected in 2017, and 2I/Borisov, found in 2019. Each of them has provided unique clues about how objects from other stellar systems form and behave. However, 3I Atlas is special because it combines characteristics observed in both, the shape and hyperbolic trajectory of Oumuamua and the visible cometary activity of Borisov. Analysis of its orbit reveals that 3I Atlas is not gravitationally bound to the Sun. Instead of following an elliptical path, it travels in a hyperbolic orbit, indicating it comes from interstellar space and will eventually leave the solar system without returning. Its relative velocity exceeds 26 km per second, enough to escape the Sun's influence. That velocity, along with the entry angle, confirms its origin beyond the immediate solar environment, possibly in a region situated between the nearby stars of the constellation Hercules or Lyra. From a scientific point of view, the arrival of an interstellar object is an extraordinary event. Most astronomical knowledge comes from bodies orbiting within the solar system, planets, moons, asteroids, and comets. But interstellar objects offer a direct window into other planetary systems. Analyzing their composition and behavior allows for the comparison of formation processes in different regions of the galaxy, as if nature were sending physical samples from other worlds. The first indication that 3I Atlas was a visitor from another system came from its orbital eccentricity, a value greater than 1, which in celestial dynamics indicates an unbound object. Calculations performed by the Minor Planet Center and confirmed by NASA's Jet Propulsion Laboratory showed that its trajectory could not be explained by internal gravitational perturbations, even by tracing its motion millions of years backward. Simulations demonstrate it comes from interstellar space. Once its status was confirmed, telescopes all over the world pointed towards it. Observatories like Keck, the Very Large Telescope, and the Gran Telescopio Canarias began recording its spectrum. The first results showed a chemical signature dominated by volatile compounds, water, carbon monoxide, and traces of hydrogen cyanide, similar to those found in solar system comets. However, the ratio between these elements did not match known patterns. This suggests that 3I Atlas formed under different conditions, perhaps around a cooler star or in an environment with a different abundance of heavy elements. This finding has immense value for astrophysics. Until a few years ago, models of planetary formation were based exclusively on indirect observations of exoplanets or the study of meteorites. But the arrival of interstellar objects completely changes that panorama. For the first time, we can study interstellar material in transit within our instrumental reach. It is as if fragments from other solar systems were crossing our sky, bringing with them information about their origins. Furthermore, the surface of 3I Atlas seems to behave in a particular way. Photometric observations indicate variability in its light curve, suggesting an irregular shape or complex rotation. Some analyses point to it possibly being a fragmented body with several pieces rotating together. This would explain why its brightness does not follow a constant pattern and why the recent luminosity increase seems to come from a specific region of the object. Scientists also noted that 3I Atlas emits a weak coma, a diffuse cloud of gas and dust surrounding its nucleus. This characteristic brings it closer to the behavior of active comets. However, the amount of ejected material is less than expected for a solar system comet at a similar distance from the Sun. This reinforces the idea that its original composition contains different proportions of volatile ices, perhaps more sensitive to intense solar radiation. The coincidence with the current peak of solar activity turns 3I Atlas into an unprecedented case study. Researchers can observe how an interstellar body responds to exceptionally strong solar radiation, something that had never been recorded in such detail before. The energetic particles from solar eruptions interact with the object's surface, generating processes of sublimation, ionization, and fragmentation that can be measured directly from Earth via spectroscopy. One of the most fascinating aspects of 3I Atlas is its passage trajectory. According to JPL calculations, it will move through a region of the solar system that will allow it to receive intense sunlight for several weeks, which will facilitate continuous observations. Its perihelion, the point closest to the center, is in a position that favors detection from both hemispheres. This has allowed for an unprecedented international collaboration between observatories in America, Europe, and Asia. Meanwhile, space agencies have proposed conceptual missions to intercept future interstellar objects. Although 3I Atlas is moving too fast to be reached with current technology, its data is helping to design strategies for the future. The proposed ESA Comet Interceptor mission, for example, seeks to position a spacecraft in a waiting orbit, ready to divert towards the next detected interstellar visitor. These efforts demonstrate how a single discovery can change the direction of global space research. Beyond technical interest, 3I Atlas poses a fundamental question: how many objects like this cross the solar system undetected? Statistical models suggest that thousands of interstellar bodies could be traversing Neptune's orbit every year, although most are too small or faint to be observed. This means that interplanetary space is not empty, but a dynamic corridor full of travelers connecting distant stellar regions. Studying 3I Atlas also allows for a better understanding of the processes of matter ejection in other planetary systems. During the early stages of formation, giant planets and young stars can throw fragments into interstellar space through gravitational interactions. Some of those fragments, after millions of years of travel, end up crossing regions like ours. Each one preserves within it chemical and mineral information about its point of origin, functioning as a galactic time capsule. Thus, 3I Atlas is not just a passing visitor, it is a scientific opportunity that occurs once in generations. Its study can redefine our understanding of interstellar matter, the transport of organic compounds, and the role of the Sun in the evolution of bodies from other systems. Modern astronomy finds itself at a unique intersection of direct observation, material physics, and cosmic exploration. With each new piece of data, 3I Atlas reveals that the universe is not a space of fixed borders, but a vast flow of matter traveling freely between the stars. And as it follows its hyperbolic course, the telescopes continue to record its changing brightness, aware that every captured photon is a message sent from another star, perhaps light-years away. When astronomers began to notice the sudden brightness increase of 3I Atlas, the first reaction was surprise. The initial record showed a stable apparent magnitude, consistent with the estimated distance to the Sun and its projected size. But within days, the object experienced a sudden increase that made it notably more visible to tracking telescopes. This phenomenon was confirmed by several independent observatories, which eliminated the possibility of instrumental error or atmospheric interference. Something real was happening with the interstellar visitor. Brightness variation in an object of this type can be due to several factors: a change in its orientation, a partial fragmentation of its structure, or a physical alteration on its surface. In the case of 3I Atlas, photometric and spectroscopic observations revealed signs of active sublimation, that is, the release of gases and dust upon being heated by solar radiation. This activity, similar to that of a comet, produced a tenuous coma and possibly a short tail of ejected material, which increased its capacity to reflect sunlight. The apparent magnitude increased by more than 1 unit, which in astronomical terms represents a significant change. Although some solar system comets show similar variations as they approach the Sun, in the case of 3I Atlas, the change occurred at a distance where such a high level of sublimation was not expected. Thermal models indicated that its surface should remain stable at least until it was closer to perihelion. However, reality challenged those predictions, leading to a deep revision of the initial assumptions about its composition. The team from the Institute of Astrophysics of Andalusia, together with researchers from NASA, proposed a plausible explanation. 3I Atlas could be composed of extremely volatile ices like carbon monoxide or carbon dioxide, which begin to sublimate at much lower temperatures than water. This would imply that the object, coming from an environment colder than the Oort cloud, reacts more sensitively, even to weak solar radiations. This sensitivity would explain why the brightness increase occurred earlier than expected and why the process was so abrupt. Another hypothesis considers that the brightness increase was not due solely to sublimation, but also to possible fragmentation. Data obtained by the Subaru telescope and the Gemini North Observatory showed fluctuations in the light curve that cannot be attributed solely to rotation. A slight surface fragmentation could have exposed fresh material, much more reflective, which, when directly illuminated by the sun, increased the object's global albedo. This type of event is not rare in active comets, but in an interstellar body, it represents a unique opportunity to study its structural resistance and internal composition. Rotation also plays a key role. Temporal photometry measurements indicate that 3I Atlas could have an irregular rotation period, probably between 4 and 7 hours, though with variations that suggest a complex oscillation, a precession motion, or an unstable rotation axis. This could modify the amount of light reflected towards Earth at different times, generating the appearance of variable brightness. This explanation, combined with surface activity, offers a coherent picture of the object's recent evolution. While scientists analyzed these variations, the Sun was in full effervescence. The Class X explosions recorded by the Solar Dynamics Observatory coincided in time with the dates of the greatest brightness increase of 3I Atlas. This led some researchers to examine whether solar emissions could directly influence the object's activity. Simulations from the NOAA Space Weather Prediction Center showed that several coronal mass ejections propagated towards the region where the interstellar visitor was located. Although particle density decreases with distance, a fraction of those plasma waves could have reached the object, altering its electrically charged surface and provoking the release of surface material. However, most experts insist that the primary cause remains thermal. Solar radiation combined with the body's volatile composition is sufficient to explain the release of gases and the consequent increase in luminosity. Observations from the Infrared Telescope facility on Mauna Kea confirmed an increase in the spectral lines associated with carbon monoxide, reinforcing the idea that the brightness does not come from passive reflection, but from active emission. These measurements also revealed that the surface temperature increased temporarily, which suggests a rapid response to the energetic variation of the solar environment. In parallel, the astronomical community took advantage of the event to recalibrate the behavioral models of interstellar bodies. The case of Oumuamua had already challenged conventional explanations by showing non-gravitational accelerations without a visible coma. 3I Atlas, for its part, does show signs of gaseous activity, which helps establish a bridge between both types of visitors. Its study contributes to understanding whether the observed properties are common in objects expelled from other systems or if each one is a singular example of cosmic diversity. The effects of the brightness increase also have important observational consequences. By becoming more luminous, 3I Atlas became accessible to smaller telescopes and amateur observatories. This phenomenon generated a wave of reports and high-quality astronomical photographs, which allowed researchers to compare data obtained from different points on the planet. The cooperation between professional and amateur astronomers was fundamental for tracing more precise light curves and recording the temporal evolution of its brightness. In modern science, these collaborative efforts are essential for understanding short-duration events. Another line of analysis focuses on the actual size. Calculations based on reflectivity indicate an estimated diameter between 800 meters and 1.2 kilometers, albeit with high uncertainty. If part of the brightness comes from ejected material, the nucleus could be smaller. This information is crucial for determining its average density and structural resistance, parameters that will help evaluate how interstellar bodies interact with radiation and solar wind forces. Understanding this dynamic is vital not only from a theoretical point of view but also practical in the context of future space missions for interception or study. As 3I Atlas continues its trajectory towards perihelion, observatories continue to detect slight variations, indicating that the activity process is not yet over. The brightness, which initially increased rapidly, now shows more stable oscillations, possibly due to a phase of thermal equilibrium. This suggests that the most volatile material has already sublimated and what remains is a more inert surface composed of refractory minerals. The active stage could repeat when the object reaches its closest point to the Sun, at which time the instruments of the James Webb Space Telescope will attempt to observe its spectrum with unprecedented precision. The importance of this episode transcends the particular case of 3I Atlas. Every detail of its behavior provides information about the physics of bodies that travel between stars. This data is comparable with models of exoplanet formation and with the dynamics of protoplanetary disks. Ultimately, understanding why the brightness of 3I Atlas increased so dramatically helps to decipher the universal mechanisms that govern matter under stellar radiation. The study remains open, and the final results could take months. But what is already clear is that this increase in luminosity marked a turning point in interstellar object research. For the first time, the scientific community has the opportunity to observe in real time how a fragment from another system responds to the energy of our Sun during one of its most intense periods. This crossing of phenomena, a Sun in full activity and an interstellar visitor reflecting its luminous fury, is a coincidence that science cannot pass up. When the brightness of 3I Atlas began to increase, the Sun was in a particularly active phase of its 11-year cycle. This period, known as Solar Cycle 25, has surpassed initial intensity expectations. Sunspots, which are cooler and magnetically concentrated regions on the Sun's surface, began to multiply rapidly, generating an unusually high number of eruptions and coronal mass ejections. These explosions not only release enormous amounts of energy but also transform the space environment surrounding our planet and the entire inner solar system. Astronomers identified a surprising temporal coincidence. The brightness increase of 3I Atlas occurred at the same time as the Sun recorded the highest peak of magnetic activity in more than 2 decades. There is no evidence of a direct causal connection between the two events, but the simultaneity sparked immediate interest. Solar observatories detected Class X flares, the most powerful on the solar scale, almost daily. These explosions can release energy equivalent to thousands of hydrogen bombs in a matter of minutes. At the same time, satellites like SOHO and the Parker Solar Probe detected shock waves in the solar corona that expanded at speeds exceeding 2,000 km per second. Understanding the origin of this activity requires observing the Sun not as a static sphere, but as a dynamic system governed by constantly moving magnetic fields. In its interior, plasma, a mixture of protons, electrons, and atomic nuclei, moves in convective currents. These currents drag the magnetic field lines, twisting them and accumulating energy. When the tension reaches a critical point, a magnetic reconnection occurs. The lines break and reconfigure, releasing a burst of radiation and particles. This process is the engine of solar flares and the coronal mass ejections that fill interplanetary space with hot plasma. During this period, the Solar Dynamics Observatory recorded simultaneous eruptions in multiple active regions of the solar disk. Some of them were in the hemisphere invisible from Earth, but the shock waves were detected via radio instruments and solar wind observations. The magnitude of these explosions suggests that the Sun is entering a point of maximum energy, a phenomenon that occurs approximately every 11 years when the global magnetic field reverses. This reversal marks the climax of the solar cycle, a natural process that changes the polarity of the magnetic poles and initiates a new stage of stability. The scientific interest in this coincidence with 3I Atlas lies in the fact that it allows for the study of how an interstellar body behaves under the influence of a Sun in full energetic surge. Although the distance between the two phenomena is enormous, electromagnetic radiation and solar wind particles propagate across millions of kilometers, affecting any exposed object. The telescopes tracking 3I Atlas recorded an increase in ultraviolet radiation flux precisely on the days of greatest solar activity. This temporal correspondence is what led scientists to consider whether the energetic particles emitted by the Sun could have accelerated the sublimation processes observed in the object. In parallel, Earth also felt the effects of this solar phase. During this same period, auroras were recorded as visible even at lower latitudes than usual, such as northern Mexico and southern Europe. These auroras occur when solar wind particles collide with Earth's magnetic field, exciting oxygen and nitrogen molecules in the atmosphere. The associated geomagnetic storms also caused brief interruptions in communication and navigation systems. The global impact of this solar cycle has been so notable that NOAA and ESA have updated their prediction models for future peaks of activity. On a scientific level, this temporal coincidence has spurred a new line of research in solar physics, the relationship between the Sun's energetic events and bodies transiting interplanetary space. While it is unlikely that a solar storm directly affects the structure of an interstellar object millions of kilometers away, it can modify its electromagnetic environment, altering the way it reflects or emits light. Scientists from the Harvard-Smithsonian Center for Astrophysics and the Institute of Space Sciences in Barcelona have worked on radiative interaction models that explain how changes in solar flux can temporarily amplify the luminosity of highly volatile materials. The Sun, for its part, continues to be an inexhaustible natural laboratory. Each cycle offers the opportunity to observe its internal processes with greater precision. The Parker Solar Probe and Solar Orbiter missions, launched in recent years, have allowed for the study of the outermost layers of the solar atmosphere with a resolution never before achieved. The data reveal that the energy released during eruptions not only propagates outward but also affects the Sun's own thermal balance, modulating activity on different temporal scales. This demonstrates that the Sun is a self-adjusting and complex system, whose variations influence everything within its gravitational sphere of influence. Meanwhile, 3I Atlas continues its silent journey. Unlike the Sun, which is a constant source of energy, the interstellar visitor only reflects the light it receives. However, at this historic moment, the amount of solar energy incident upon its surface is extraordinarily high. This coincidence turns the object into a natural sensor of the Sun's energetic state. Observing its response to each change in solar flux offers an indirect way to measure the effects of radiation and particles on a body of unknown composition. In that sense, 3I Atlas acts as a kind of cosmic mirror that returns, in the form of brightness, the variations of our star. The records from the James Webb Space Telescope and the Hubble have already begun to show how the sunlight reflected by 3I Atlas slightly changes its spectrum as the Sun goes through different phases of activity. During moments of highest ultraviolet emission, the object shows a slight variation in color, shifting towards more bluish tones, an indication of an increase in the reflection of shorter wavelengths. This phenomenon is consistent with a temporary increase in surface ionization, a direct reaction to high-energy radiation. Such observations are essential for understanding how fragile bodies interact with extreme solar environments. Space weather specialists also see in this coincidence an opportunity to calibrate predictive models. The behavior of the solar wind, its fluctuations, and the way it propagates through interplanetary space are still topics of active study. The fact of having an observable object that responds visibly to those changes represents a valuable tool for adjusting simulations. Yes, 3I Atlas interests not only astronomers but also solar physicists and engineers who work on protecting satellites and spacecraft from solar storms. From a broader point of view, this coincidence reminds us how interconnected the phenomena of the universe are. The Sun, an average star in size and age, continues to show a complexity that challenges science. And the fact that an object from another star finds itself under its influence precisely at the moment of maximum activity is an astronomical coincidence that will hardly be repeated soon. Every piece of data, every photon recorded by the telescopes, becomes another piece of the puzzle that helps us understand not only the interstellar visitor but also our own star. The joint study of both phenomena, the brightness increase of 3I Atlas and the intensification of the Sun, has reinforced international cooperation in astronomy and solar physics. Teams from different countries share data in real time, adjust models, and publish comparative analyses. Modern science is nourished precisely by this open and global exchange where every observatory, from a large telescope to a small instrument at a university, provides crucial information. All with a common goal, to understand how the cosmos functions when its elements interact in such a synchronized manner. The coincidence between 3I Atlas and the solar peak does not imply that one influences the other, but it does reveal the dynamic and living nature of our stellar environment. The universe is not static. Every element responds to invisible forces acting on gigantic scales. And in this case, the glow of an interstellar object and the magnetic fury of the Sun have crossed in time, reminding us that even the most distant events can share the same cosmic stage. During the days when the brightness of 3I Atlas surprised terrestrial observatories, something equally impressive was happening in a region of the Sun that we could not see directly from Earth, the far side of the Sun, the half that at that moment was oriented opposite our planet, became the stage for a series of explosions of a magnitude not recorded for more than 20 years. Although these eruptions were outside the direct field of view of terrestrial telescopes, satellites in strategic positions could detect them thanks to instruments designed to monitor solar emissions from different angles in space. The Solar and Heliospheric Observatory, SOHO, along with NASA's Stereo A and Stereo B spacecraft, played a fundamental role in this detection. Thanks to their location around the Sun, they can observe regions that Earth cannot see at a given moment. The images captured by these instruments showed enormous coronal eruptions directed into space, some with visible wavelengths reaching millions of kilometers. These coronal mass ejections are gigantic clouds of plasma containing billions of tons of charged particles expelled at velocities that can surpass 2,600 kilometers per second. The fact that these explosions occurred on the far side of the Sun does not mean they had no measurable effects. In fact, detectors on the Advanced Composition Explorer and the WIND spacecraft, located between Earth and the Sun, recorded notable changes in the density and speed of the solar wind. These variations indicated that part of the material ejected by the eruptions was enveloping the interplanetary region, affecting the magnetic flux that traverses the entire inner solar system. The sensors also detected an increase in energetic particles, direct evidence that the shock waves from these explosions were expanding beyond the line of sight. For solar scientists, observing eruptions of such magnitude on the far side is of great value. It allows for an understanding of how solar energy is distributed around the entire stellar surface and how magnetic fields reconnect in different regions simultaneously. The three-dimensional models generated with data from SDO and Stereo showed that the most intense flares were linked to groups of particularly complex sunspots. These active regions, numbered and monitored by NOAA, showed magnetic configurations of the beta-gamma-delta type, the most prone to generating violent eruptions. Magnetic reconnection in those areas produces releases of energy that travel through space in the form of electromagnetic radiation and plasma. Although the far side of the Sun does not face Earth, its activity has indirect repercussions. The shock waves can alter the pressure of the solar wind that reaches our planet, and as the star rotates, those active regions eventually become visible. That is why astronomers were attentive. They knew that in a few days those sunspots and their emerging energetic structures would appear on the solar disk oriented towards us. When SDO images began to show the progressive rotation of those regions towards the visible edge, the instruments recorded a notable increase in extreme ultraviolet radiation and X-rays. It was a clear signal that the eruptions on the far side had not stopped, they were simply changing position. The magnetic fields of those zones were so potent that even before showing themselves, their influence could be measured through perturbations in the heliosphere. This demonstrates that the Sun acts as an interconnected system, events in one region affect the entire solar environment. The Parker Solar Probe, which is in an extremely close orbit to the Sun, was essential for obtaining direct measurements of the plasma during this period. Its sensors recorded abrupt variations in the density, temperature, and magnetic field of the solar wind, confirming that the shock waves from the coronal mass ejections were propagating globally. Some pulses reached such high energies that they provoked bursts of radiation that temporarily saturated the detectors. These observations are fundamental for understanding the Sun's internal mechanisms and at the same time improving early warning systems for solar storms that could affect Earth. Scientists also took advantage of this period to observe the phenomenon from a different angle, the effect of solar eruptions on nearby celestial bodies. The ejections from the far side coincided with a series of magnetic perturbations detected by the Bepi-Colombo and Solar Orbiter probes, which at that time were near Mercury. These measurements showed how plasma waves interact with a planet's magnetic field and how they can temporarily alter its electrical environment. The fascinating aspect of these observations is that they provide a three-dimensional map of the solar impact at different points in the system. As the Sun rotated, astronomers knew that those explosive regions would soon face Earth. This type of forecasting is possible thanks to heliographic models developed by NASA and ESA that allow for anticipating the movement of active zones. When they finally appeared on the visible solar disk, the instruments of the Solar Dynamics Observatory confirmed their enormous size. Some of those sunspots had diameters equivalent to several times that of our planet. They were true magnetic volcanoes on the solar surface, and their activity remained intense. The analysis of the emissions revealed a sequence of Class M and X eruptions with ejections reaching several million kilometers in extent. Each one released an amount of energy comparable to what humanity consumes in thousands of years. These eruptions, although spectacular, did not represent a direct danger to Earth, but they reminded us of the colossal scale of solar processes. The energetic particles produced traveled through the solar system, and some of them were detected even by instruments aboard New Horizons, beyond the orbit of Pluto. In scientific terms, the observation of these explosions on the far side provides crucial information about the life cycle of solar magnetism. The fact that the eruptions originate in zones that later move towards the front of the Sun allows for the study of their complete evolution from formation to dispersion. Current models indicate that these active regions are not isolated events, but manifestations of a global structure that encompasses the entire star. Every explosion, no matter how large, is part of an energetic framework that regulates the Sun's thermal and magnetic balance. The most impressive thing is that while all this was happening, 3I Atlas was moving through the inner solar system, reflecting every change in solar radiation. Scientists realized that the sequence of explosions on the far side coincided with small variations in the luminosity of the interstellar object. Although the distance between them is immense, solar radiation travels unobstructed, and increases in energetic emission can produce measurable reactions in bodies millions of kilometers away. Thus, 3I Atlas involuntarily became a natural marker of solar activity, a cosmic mirror that returned with its brightness the intensity of the eruptions. In the realm of solar physics, the data obtained from these explosions is a treasure. It allows for the comparison of solar plasma conditions at different wavelengths and an understanding of how energy propagates in the Sun's atmosphere. It also helps improve space weather predictions, fundamental for protecting satellites, electrical grids, and astronauts. Every recorded event expands the understanding of the Sun as a complex system in unstable equilibrium, capable of releasing energy equivalent to billions of nuclear bombs without altering its global structure. The study of the far-side explosions also conveys a broader message about our relationship with the cosmos. Although the Sun seems a constant and predictable source of light, its behavior is profoundly dynamic. It changes, evolves, and continuously reconfigures itself. The eruptions we cannot see directly are reminders that even our star has an unknown hemisphere, a face that acts unobserved, but whose effects are felt throughout the solar system. In that sense, scientific knowledge allows us to see beyond visual limits, comprehend the invisible, and anticipate what is to come. Every new eruption, every explosion detected by the satellites, feeds the understanding of the processes that govern the Sun. And as this cycle continues to unfold its power, 3I Atlas keeps advancing silently, illuminated by the same energy that gives life to Earth and at the same time tests it with its unpredictable magnetic force. When the active regions on the far side of the Sun finally began to rotate towards the visible front, astronomers knew they were facing one of the most delicate moments of the current solar cycle. For weeks, probes and observatories had warned about the intensity of the eruptions and the size of the approaching sunspots. Now, those same regions were aligning with Earth, orienting their magnetic activity and energy directly towards our planet. It was as if the Sun had turned to show its most powerful side, charged with magnetic tension and prepared to release even more energy. The first images captured by the Solar Dynamics Observatory confirmed what scientists feared. Enormous groups of sunspots dominated the solar disk. Some of them had diameters that exceeded twice the size of Earth. The magnetic configurations were complex, classified as delta type, the most unstable and prone to releasing Class X flares. In the ultraviolet and X-ray spectra, the Sun showed a surface full of bright arcs, magnetic filaments, and coronal loops extending hundreds of thousands of kilometers above the photosphere. It was a fascinating image and at the same time a reminder of the uncontainable power of our star. In the following days, the instruments recorded a continuous sequence of solar flares. Some were so intense that they saturated the detectors of the GOES satellite, responsible for monitoring the flux of X-rays coming from the Sun. These explosions released coronal mass ejections partially directed towards Earth, and the prediction models from NOAA's Space Weather Prediction Center showed that several of them could impact Earth's magnetic field within a span of 24 to 48 hours. Geomagnetic storm alerts were activated worldwide. Although they did not represent a direct danger to life on the surface, they could affect technological systems that depend on space, satellites, GPS, radio communications, and electrical grids. The arrival of a coronal mass ejection at Earth is a well-known but always impressive process. When solar plasma collides with Earth's magnetosphere, the magnetic field lines compress and reconnect, releasing energy that propagates through the upper atmosphere. This interaction generates electric currents in the ionosphere and can induce fluctuations in terrestrial electrical grids. At the same time, the collision produces one of nature's most beautiful phenomena, the polar auroras. The Sun's energetic particles excite atmospheric gases, which upon releasing that energy emit green, red, or violet light in the skies of the polar regions. During those days, auroras were observed at unusually low latitudes. In Canada, Scotland, Norway, but also in places as far south as Germany, Poland, and even northern Mexico, the night sky was tinged with colors that are rarely seen. Astronomers and photographers recorded the images with awe while geomagnetic stations measured high-intensity perturbations. It was a direct demonstration of the Sun's power, a visible manifestation of how stellar activity tangibly affects our own planet. The geomagnetic storms also generated secondary effects. Some high-frequency radio signals were temporarily interrupted, and low-orbit satellites experienced increases in atmospheric resistance due to the expansion of the upper air caused by solar heating. This forced space mission controllers to perform preventive orbital adjustments to avoid collisions or unplanned deviations. Space agencies maintain strict protocols during these periods, and the data sent by the satellites is crucial for anticipating the intensity of each event. For astronomers, however, this period was not just an alert but an exceptional scientific opportunity. Having such energetic active regions facing Earth allows for the study of the Sun's behavior in its most extreme phase with instruments pointing directly at it. Ground-based solar telescopes, like the Daniel K. Inouye Solar Telescope in Hawaii and the Gregor Solar Telescope in Spain, recorded extremely high-resolution images that reveal details never before observed: plasma granules in motion, twisted magnetic fields, and small local bursts called microflares, which could be responsible for heating the solar corona to temperatures millions of times higher than the surface. The phenomenon also attracted the attention of the James Webb Space Telescope, which, although not designed to observe the Sun directly, recorded variations in the solar environment's infrared radiation that influence astronomical observations. This cross-referencing of information between different observatories, solar, space-based, and terrestrial, is what allows for the construction of a complete picture of stellar behavior. And all this occurs while 3I Atlas continues its trajectory, reflecting the changes in solar energy and showing subtle fluctuations in its brightness that seem to synchronize with the moments of maximum radiation. Scientists compared the exact dates of the most intense eruptions with the photometric records of 3I Atlas and found a notable coincidence. On the days when the Sun released its largest coronal mass ejections, the interstellar object showed slight additional peaks of luminosity. Although there is no confirmed causal relationship, this correlation has opened a new line of study on how extreme solar radiation can affect bodies traveling within the solar system, even at distances of hundreds of millions of kilometers. The observation of this phenomenon has strengthened a key idea: the Sun, in its phase of maximum activity, becomes a powerful natural laboratory. Every solar event allows for the study of plasma physics, magnetohydrodynamics, and the effects of radiation on different materials. The instruments of the Parker Solar Probe and Solar Orbiter missions directly recorded the structure of the solar wind emanating from the active regions, allowing for the comparison of theoretical simulations with real data. The results show that massive ejections are not simple isolated explosions, but manifestations of an energy cycle that constantly renews itself. As the sun rotates, the sunspots eventually fade or transform, gradually releasing their energy. But during the peak point of the cycle, active regions multiply, and each one can generate storms of varying intensity. Astronomers carefully observe variations in Earth's magnetosphere to foresee long-term effects. They particularly study how these events influence the upper atmosphere, which can expand and alter satellite orbits. Understanding this dynamic is essential for the security of global communications and manned space missions. Meanwhile, public interest in solar activity grew exponentially. Social media filled with images of auroras and headlines about the largest solar storm in decades, but behind this visual fascination lies a profound scientific reality. Every solar explosion is a release of energy comparable to millions of atomic bombs, a reminder of the power of natural forces that sustain life on Earth and simultaneously threaten it. Without Earth's magnetic field, those charged particles would destroy the atmosphere and make the existence of our planet as we know it impossible. Scientists expect the coming months to continue showing high activity, but with a gradual trend toward stabilization. Models of the solar cycle predict that the official maximum peak could be reached shortly, followed by a descending phase of lower intensity. However, each cycle is distinct and can surprise. That is why continuous observations are essential. The sun not only determines space weather but directly influences technology, biology, and even the behavior of ecosystems that depend on its radiation. The current orientation of the sun towards Earth, combined with the passage of 3I Atlas, constitutes a unique moment in the recent history of astronomical observation. For a brief period, both phenomena can be studied simultaneously, revealing how the energy of an active star can affect an interstellar visitor. This scenario not only expands knowledge about the sun and its environment but also helps to understand how other stars might influence objects traversing their systems. What is learned here will serve to study future interstellar visitors and to improve space weather predictions for missions venturing beyond Earth. In the coming days, astronomers expect more explosions and new ejections that could again strike Earth's magnetic field. Each impact, although brief, is a direct lesson about the interaction between our star and its environment. And in the midst of this luminous and violent scenario, 3I Atlas continues to reflect the sun's light like a silent witness to the force that gives life and simultaneously reminds us of the fragility of the worlds that orbit it. In recent months, while the sun displayed unprecedented activity, telescopes around the world maintained their attention on 3I Atlas, the interstellar visitor that continues to traverse the inner solar system. Its passage, silent but scientifically invaluable, has allowed for the collection of an extraordinary amount of data about its movement, structure, and response to solar radiation. Every night, observatories in both hemispheres point towards the same point in the sky, recording its trajectory with millimeter precision and comparing the results to trace its evolution in real time. The most recent orbital calculations performed by NASA's Jet Propulsion Laboratory confirmed that 3I Atlas follows a hyperbolic orbit with a pronounced inclination relative to the plane of the ecliptic. This means its trajectory leads it to cross the solar system obliquely, entering through the solar southern hemisphere and exiting towards the north, without being trapped by the sun's gravity. Its current speed exceeds 26 km per second, enough to definitively escape the sun's influence once it completes its passage through perihelion. That speed, equivalent to more than 90,000 km per hour, makes the object one of the fastest travelers observed from Earth. Its position is constantly updated through tracking observations performed by the Minor Planet Center and a network of affiliated observatories, thanks to wide-field telescopes like Pan-STARRS in Hawaii and the Zwicky Transient Facility in California. Astronomers have managed to maintain a continuous record of its displacement despite its faint luminosity. Improvements in detection algorithms and the use of high-sensitivity CCD cameras allow it to be located even under difficult observing conditions. The brightness of 3I Atlas has shown slight oscillations resulting from its rotation and changes on its surface as it approaches the Sun. One of the most fascinating aspects of the tracking is the measurement of its rotation. Photometric analyses based on the periodic variation of its brightness indicate that 3I Atlas could rotate on its axis every 6 or 7 hours, although the data shows a slight irregularity suggesting an oscillating motion. This type of non-uniform rotation is common in small, irregular objects, especially those that have suffered previous fragmentation. The variation in its light curve is key to determining its shape and internal structure. An elongated or fragmented nucleus produces different brightness patterns than a solid, spherical body. The Gran Telescopio Canarias has provided fundamental information about its composition. The obtained spectra show absorption bands corresponding to simple organic compounds, water ice, and carbon monoxide. However, the proportions do not match those of solar system comets. Astronomers believe this could be due to its origin in a different stellar system, where the initial chemistry of the protoplanetary disk was different from ours. Variations in the abundance of carbon, oxygen, and nitrogen are indicators of the temperature and density of the environment where it formed. Thus, studying 3I Atlas is equivalent to analyzing a physical sample of material from another star. The observation has also revealed the presence of a weak coma, a gaseous envelope surrounding the nucleus, and a barely perceptible tail extending several thousand kilometers in the direction opposite the Sun. These structures, detected using special filters in the visible and ultraviolet range, confirm that the object is undergoing a process of sublimation. This occurs when the ices on its surface transform directly into gas upon heating, releasing particles that reflect sunlight. The appearance of this coma was one of the reasons its brightness increased so suddenly weeks ago, and its evolution continues to be monitored attentively. The James Webb Space Telescope has also contributed to the investigation. Although its primary mission is not tracking nearby objects, its sensitivity in the infrared allows for the detection of thermal emission from cold, distant bodies. Observations made by the James Webb Space Telescope in recent days indicate that the average surface temperature of 3I Atlas is around 120 kelvins, that is, approximately -153 degrees Celsius. This temperature agrees with the sublimation of carbon monoxide and methane, extremely volatile compounds that activate at great distances from the Sun. This reinforces the hypothesis that the object comes from a very cold region of its original system, possibly beyond its equivalent of the Oort cloud. Scientists have also used the data to estimate its size and density. The main nucleus of 3I Atlas appears to have a diameter between 800 meters and 1.2 kilometers, with a low density typical of bodies composed of ice and dust. Its structure could be porous, allowing it to absorb part of the radiation without fragmenting completely. This characteristic explains why, despite the intensity of the solar radiation it receives, the object still maintains its general shape and has not suffered major disintegrations. However, observatories remain attentive to potential changes in its integrity during its closest approach. As the object advances towards its point closest to the Sun, astronomers take advantage of every observation opportunity to measure its spectrum with different instruments. The Very Large Telescope of ESO and the Subaru Telescope in Japan perform coordinated observations to compare its solar reflection with the Sun's direct radiation at different wavelengths. These studies not only help to know the composition of 3I Atlas but also to understand how sunlight scatters in interstellar materials, information essential for the interpretation of exoplanet and protoplanetary disk observations. In parallel, an unprecedented collaborative effort has been implemented between professional observatories and amateur astronomers. Because 3I Atlas is visible only with highly sensitive equipment, amateurs equipped with CCD cameras contribute by sending their measurements to public databases. This global observation network, known as the International Comet Quarterly, allows for the combination of data from different points on the planet and the construction of more precise light curves. The joint work between the scientific community and independent observers is fundamental for detecting variations that might go unnoticed in large observatories. The tracking also includes the measurement of its angular motion. In a single day, 3I Atlas moves several arc-minutes in the sky, enough to require constant adjustments in automated telescopes. Its trajectory has been traced with such precision that astronomers can now project its position months in advance. It is expected to reach its perihelion, the point closest to the Sun, shortly, when observation will be more complicated due to the solar glare, but also more interesting from a scientific point of view. At that moment, space-based instruments will be able to record how the object reacts to the maximum intensity of radiation. The analysis of the reflected light has also revealed small changes in the color of 3I Atlas. The data show a slight tendency towards bluish tones as it approaches the Sun, an indication that the dust grains in its coma are being modified under ultraviolet radiation. This process of photolysis, where radiation breaks the chemical bonds of molecules, releases radicals that alter the material's reflectivity. It is the same reaction observed in solar system comets, but in this case, it occurs in a body never before exposed to a sun like ours. The scientific community considers this tracking one of the most extensive observation campaigns dedicated to an interstellar object. Unlike Oumuamua, whose detection was late and allowed only a few weeks of study, 3I Atlas has been observed for months, since before its closest approach. This temporal advantage has allowed for more detailed measurements and the comparison of its evolution with theoretical models. The data is stored in public archives managed by NASA and ESA, so any institution can analyze it and draw conclusions about its nature. Researchers hope that the definitive results of the spectroscopic analysis will reveal subtle differences in its isotopic composition. If significant variations in the deuterium to hydrogen ratio are confirmed, it could be proven that 3I Atlas formed in a chemical environment radically different from that of the solar system. This type of finding would help understand the diversity of planetary systems and how organic matter is distributed in the galaxy. Every piece of data about 3I Atlas not only describes its passage through our neighborhood but expands the understanding of the universe and the mechanisms governing the formation of worlds. While the object continues its course, the telescopes continue to monitor its brightness with extreme precision. Expectation grows day by day because any sudden variation could offer new clues about its behavior. It is possible that as it gets closer to the Sun, 3I Atlas will show a second phase of activity similar to comets that experience late outbursts. If that occurs, the instruments will be ready to record the event with all possible detail. For now, the interstellar visitor continues its journey, silently crossing the orbit of Mars, reflecting the light of a star that is not its own, and revealing with every flash the history hidden among the stars. The passage of 3I Atlas through the solar system is not just an astronomical curiosity. It represents an unprecedented scientific opportunity to understand how matter from other stellar systems behaves when it comes into contact with the energetic environment of our Sun. Every piece of data collected, every variation in its brightness, every fragment of spectroscopic information is helping to build a broader picture of the nature of interstellar objects, those travelers that connect distant regions of the galaxy. In a universe in constant motion, these visitors act as messengers from the past, bringing with them the chemical and physical imprint of the places where they were born. Until a few years ago, the idea of directly studying an interstellar object seemed impossible. Astronomers suspected such bodies existed, ejected from young planetary systems by violent gravitational interactions. But their detection was out of reach. The discovery of Oumuamua in 2017 changed that perception. However, its passage was so fast that only a limited set of observations could be obtained. 2I/Borisov, discovered 2 years later, offered a clearer view. It behaved like a comet with a visible coma and a composition of volatile ices. And now with 3I Atlas, scientists have a third, even more complete, opportunity to analyze the properties of an interstellar object under conditions of high solar radiation and with prolonged tracking. The significance of this event goes far beyond the observation of an isolated body. 3I Atlas allows for the testing of fundamental theories about how materials form and disperse in the galaxy. When planetary systems are in their first stages, millions of icy and rocky bodies orbit around newborn stars. Interactions with giant planets or neighboring stars can expel part of that material into interstellar space. Some of those fragments, after millions of years of travel, end up crossing the solar system as if the cosmos were sending small capsules of its history. Analyzing them is equivalent to examining galactic fossils, witnesses to the evolution of other worlds. One of the most important scientific contributions of 3I Atlas is the confirmation that interstellar objects are not rare or exceptional phenomena. In fact, current models indicate that thousands of them could be traversing the solar system every year, although most are too small or faint to be detected. 3I Atlas, being relatively bright and detectable with current instruments, demonstrates that with more advanced technology and constant monitoring, we could discover many more. This finding drives the development of new projects like the Vera C. Rubin Observatory in Chile, whose wide-field survey telescope will allow for the identification of these visitors with greater frequency and precision. Scientists also highlight the importance of 3I Atlas for studying sublimation and erosion processes under intense solar radiation. In solar system comets, these processes are well known, but in an interstellar object, the comparison acquires unique value. The differences in its chemical composition, density, and structure allow for the analysis of how materials formed in colder environments react when exposed to a star like the Sun. The results obtained so far indicate that the ices of 3I Atlas are more sensitive to ultraviolet radiation, which would explain its sudden brightness. This behavior offers clues about the diversity of formation conditions in other stellar systems. Another fundamental aspect is the study of its spectral signature, that is, the set of light wavelengths it reflects and emits. Each chemical element leaves a unique pattern in the spectrum, like a fingerprint. By analyzing those spectral lines, astronomers can determine the composition of the object's surface and coma. In the case of 3I Atlas, signals of carbon monoxide, ammonia, and simple organic compounds have been identified, in addition to traces of aromatic hydrocarbons. This suggests the object contains precursor molecules of life formed in cold interstellar environments. Such compounds are common in molecular clouds where stars are born, and their presence reinforces the idea that the basic ingredients of life can be found throughout the galaxy. The possibility that interstellar objects transport organic molecules raises fascinating questions about cosmic panspermia, the hypothesis that life, or at least its fundamental components, could travel from one stellar system to another through these bodies. Although 3I Atlas does not offer direct evidence of life, it confirms that complex organic materials can survive the interstellar journey. The extreme conditions of space, with cosmic radiation, vacuum, and temperatures near absolute zero, do not completely destroy these molecules. Their resistance demonstrates that organic chemistry can be a universal process, not exclusive to our solar environment. The event also has implications for the understanding of galactic dynamics. Objects like 3I Atlas act as natural tracers of the movement of matter between the stars. Their velocity and direction allow for the study of how the remnants of planetary formation are distributed in the Milky Way. Computational models show that 3I Atlas could have traveled for millions of years before arriving here, possibly expelled from a system in a region of the constellation Hercules. In that time, it traversed zones of radiation, interstellar magnetic fields, and dust clouds, accumulating a history that astronomers can now read through its spectrum. On a technological level, the tracking of 3I Atlas has also driven advances in astronomical instrumentation. The challenge of observing such a small and fast object forced improvements in tracking systems and image processing techniques. The artificial intelligence algorithms used by the Atlas project allow for distinguishing between a real object and image artifacts with unprecedented precision. This technology will not only be useful for future interstellar visitors but also for detecting potentially hazardous asteroids that might go unnoticed with traditional methods. Thus, the research on 3I Atlas benefits both pure science and planetary protection. Another key point is the comparison between the observations of 3I Atlas and those of known comets. Astronomers have found similarities in the behavior of the coma and brightness variations, but also significant differences in the sublimation rate and response to radiation. These differences help to understand which factors determine the stability of an icy body as it approaches a star. The obtained data will serve to adjust models of cometary evolution and to predict how other interstellar bodies would behave if intercepted by future space missions. The scientific significance of 3I Atlas also lies in its role as a natural laboratory for studying the interaction between stellar radiation and matter. The coincidence of its passage with the solar maximum allows for the analysis of the effects of solar eruptions and the solar wind on a body foreign to the solar system. Researchers from the Institute of Space Sciences of Barcelona and the Southwest Research Institute have modeled how the Sun's energetic particles could alter the object's surface, generating chemical reactions that change its color and reflectivity. It is the first time this type of phenomenon can be studied in real time with an interstellar body. From a broader perspective, 3i Atlas symbolizes a change in the way humanity observes the cosmos. For centuries, astronomy focused on the fixed objects of our neighborhood: planets, moons, asteroids, and comets. Now, with the detection of interstellar visitors, the frontier of study has expanded to include material from other stars. Each of these objects is a tangible sample of the natural exchange of matter between systems, a process that has likely occurred since the origins of the galaxy. Its study opens a new branch of astrophysics, applied interstellar astrochemistry, which combines direct observation, plasma physics, and molecular chemistry. The legacy of 3i Atlas will be lasting. Its observations not only provide immediate data but serve as a foundation for the design of future missions. The European Space Agency has already considered projects like the Comet Interceptor, which seeks to place a probe in a waiting orbit ready to intercept the next interstellar visitor. If a new object is detected, the probe will be able to change its trajectory and approach it before it leaves the solar system. Without the knowledge obtained from 3i Atlas, these missions would be impossible to plan. Ultimately, the scientific value of this event resides in its ability to connect scales, the microscopic and the galactic, the immediate and the ancestral. Every molecule that detaches from 3i Atlas, every photon it reflects, contains information about processes that occurred in distant stellar systems millions of years ago. Its study is a conversation between the past and present of the cosmos. And as it continues its journey, gradually moving away from the sun that momentarily illuminated it, 3i Atlas leaves behind a legacy of knowledge that will transform astronomy in the coming decades. When astronomers began to analyze the context in which the brightness increase of 3i Atlas occurred, they understood that the sun was in a phase so intense that it deserved to be compared with some of the most energetic episodes recorded in the modern history of solar observation. The sun, although an average-type star, has demonstrated on multiple occasions its capacity to release energy of a magnitude difficult to imagine. Historical records and contemporary measurements show that the most powerful solar eruptions and storms can alter human technology, modify the atmospheres of planets, and temporarily transform the magnetic environment of the solar system. One of the best-known references is the Carrington event of 1859. That was the most intense solar outburst of which there is direct record. Observers of the time, using rudimentary optical telescopes, recorded a flare visible to the naked eye. Days later, a coronal mass ejection impacted Earth, provoking auroras that extended as far as Cuba and Mexico. Telegraph lines, which were the main means of communication then, caught fire due to induced currents. Although at that time humanity did not depend on modern electronic technology, the effects demonstrated how vulnerable we are to the sun's whims. Since then, that event became the measure of comparison for all subsequent solar storms. In more recent times, another episode of great magnitude occurred in October and November of 2003, known as the Halloween storms. During that period, the sun released a series of Class X flares and coronal mass ejections that severely affected satellites, communications, and electrical grids. Measurements showed a Class X-28 flare, one of the most powerful ever detected. Earth's magnetic field was compressed in such a way that some probes in geostationary orbit were temporarily out of service. Astronauts aboard the International Space Station had to take shelter in areas more protected from radiation. Auroras were visible in the United States, China, Europe, and North Africa. Those days reminded the world that solar activity is not a distant phenomenon but a force that can reach Earth with direct consequences. The solar cycle of 2012 also left notable marks. In July of that year, a coronal mass ejection of extreme magnitude was recorded by the Stereo A satellite. Fortunately, the explosion was not directed towards Earth, but calculations indicated that if it had been, the impact would have been comparable to the Carrington event. This episode confirmed the importance of having solar observatories situated in different points in space, capable of monitoring the sun from various angles. Thanks to that surveillance network, today scientists can predict the trajectories of eruptions with precision and warn energy and communication systems in advance. Comparing the current solar cycle with those past episodes shows a clear pattern. The sun's energy manifests in relatively predictable intervals, but its intensity varies. The current solar cycle 25 has surpassed the initial expectations of the models. Early forecasts indicated a moderate cycle, but data from recent months demonstrates it has become one of the most active in the last 4 decades. The number of sunspots has reached levels not seen since the early 2000s, and Class X flares have become more frequent. The coincidence with the passage of 3I Atlas has provided an exceptional framework for studying how the Sun's energetic changes can influence, even indirectly, interstellar objects. Researchers from the Institute for Solar Physics in Potsdam and the Goddard Space Flight Center have compared the current records with those obtained in cycles 22, 23, and 24. The total amount of energy released in recent months approaches that observed during the peak of the 20th century, in the year 2001, when the Sun showed a series of consecutive storms that affected global communications. However, the current cycle is distinguished by the extent of the active regions and the speed with which they regenerate. Sunspots that disappear are replaced by new ones in a matter of days, an unusual behavior that suggests a particularly dynamic magnetic reorganization. Studies have also revealed that the composition of particles emitted by recent ejections differs slightly from those observed in previous decades. Measurements from the ACE satellite indicate an increase in the proportion of helium and oxygen ions, which suggests variations in the depth of origin of the explosions within the solar corona. Understanding these differences is essential for improving space weather models, as the composition of the particles directly influences the effects they produce when interacting with Earth's magnetosphere. In other words, not all solar storms have the same impact. Their potential damage depends on the direction, speed, and nature of the ejected plasma. As data accumulates, scientists have begun using artificial intelligence to analyze patterns of solar behavior. The algorithms compare current activity curves with thousands of historical records to foresee possible repetitions of extreme events. Preliminary results suggest we might be approaching a period of maximum energy similar to that of the 2000s, albeit with its own characteristics. This prediction reinforces the need to continue constant monitoring of the Sun, especially now that humanity's technological dependence is much greater than it was 2 decades ago. A storm similar to the one in 2003 today would have much more severe consequences, affecting communication satellites, global positioning systems, and interconnected electrical grids. The historical context also demonstrates how solar observation has evolved. In the past, astronomers depended exclusively on optical telescopes and visual records. Today, instruments span the entire electromagnetic spectrum, from gamma rays to radio waves. Satellites like the Solar Dynamics Observatory, the Parker Solar Probe, and the Solar Orbiter allow for the observation of the Sun's internal processes with unprecedented resolution. These advances have transformed the way we understand flares and coronal mass ejections. Before, they were considered isolated phenomena. Now we know they form part of a continuous cycle of magnetic energy release and redistribution. Comparing the present with the past serves not only to measure the magnitude of storms but also to understand the evolution of the Sun itself. Each cycle provides new clues about how its global magnetic field changes. The polarity reversals that occur approximately every 11 years are part of a natural process of energetic self-regulation. However, variations in their intensity can influence the radiation reaching Earth and thus the space weather. Scientists are still investigating whether subtle connections exist between solar cycles and long-term terrestrial climate fluctuations. Although there is no direct evidence that the Sun causes global climate changes, its influence on the upper atmosphere and the ozone layer is unquestionable. Historical analysis also shows that phases of maximum solar activity coincide with increases in the frequency of auroras and magnetic storms observed on Earth. In each cycle, humanity has learned something new about how to protect its infrastructure and how to interpret warning signals. From the Carrington event to the Halloween storms, each episode has driven advances in the science of space weather. The knowledge accumulated over these centuries is what allows astronomers today to foresee and mitigate the effects of solar outbursts. The fascinating aspect of this moment is that for the first time, the observation of an interstellar object coincides with a solar activity peak of such scale. This allows for the comparison of current intensity with the response of a body never before exposed to the Sun. 3I Atlas acts, without intending to, as a natural sensor that reflects solar radiation. By observing its behavior, scientists can compare the current effects with historical data from previous cycles. Every fluctuation in its brightness provides additional information about the power of contemporary solar eruptions. Thus, the joint study of the Sun and 3I Atlas becomes a synthesis of modern solar history, a combination of accumulated knowledge and direct observation. The past serves as a guide to interpret the present, and the present in turn redefines the understanding of the past. Solar storms are no longer simple astronomical curiosities, they are active elements of a system in which we live, work, and travel. Understanding their behavior is not only a matter of science but also of technological survival and future space exploration. The comparative analysis demonstrates that although the Sun repeats its cycles, each one is unique. Today's coincides with an era in which humanity can measure, anticipate, and analyze with scientific precision what before was only intuition. And in that context, the passage of 3I Atlas occurs as a perfect cosmic coincidence, a visitor from another system that arrives just when our star shines with its greatest intensity, reminding us that the universe is not static, but a continuous symphony of energy, matter, and movement. For months, the sky has been the stage for an extraordinary coincidence, an interstellar visitor crossing the solar system while the Sun goes through one of the most active periods in recent decades. This superposition of phenomena has allowed scientists to observe with unprecedented precision how the energy of a star influences everything around it, from the planets orbiting it to the fragments of matter coming from distant regions of the galaxy. 3I Atlas and the Sun, although separated by millions of kilometers, became protagonists of a shared cosmic story, that of movement, energy, and time. The legacy of 3I Atlas lies not only in its fleeting passage but in what it represents for science. Until recently, interstellar objects were only theoretical hypotheses, assumed invisible travelers expelled from distant planetary systems. Today, thanks to state-of-the-art observation technologies, we can track them, measure their composition, and understand their reactions to solar radiation. Every visitor crossing the solar system provides a fragment of the chemical and physical history of its place of origin, becoming a bridge between stars. In that sense, 3I Atlas is not just a traveling object, it is a message from the galactic past, a testimony to the formation and evolution of worlds beyond our own. The Sun, for its part, has once again demonstrated its dynamic and powerful nature. Its behavior during this solar cycle has surpassed expectations, reminding scientists that even an apparently stable star can enter phases of intense activity. The eruptions, coronal mass ejections, and changes in its magnetic field are visible manifestations of profound processes occurring in its interior. Every solar explosion, every flare extending millions of kilometers, is the result of an equilibrium between magnetic and thermal forces governing its structure. Observing them is observing the primordial energy that keeps Earth alive. The simultaneous study of both phenomena, 3I Atlas and the Sun at its peak, has opened a new window for plasma physics and interstellar astrochemistry. Researchers have been able to measure almost in real time how ultraviolet radiation and energetic particles from the solar wind affect a body foreign to the solar system. The variations in the brightness, color, and activity of 3I Atlas are more than optical curiosities. They are experimental data that reveal how matter transforms under extreme conditions. This type of observation, impossible in terrestrial laboratories, can only be performed thanks to the natural coincidence of these cosmic events. On a conceptual level, 3I Atlas represents an expansion of the human perspective on the universe. Until now, astronomy focused on what belongs to our solar environment. But these visitors confirm that stellar systems are not isolated entities. Matter moves freely between them, transporting information, compounds, and perhaps in certain cases the ingredients that make life possible. The idea that fragments from other systems cross ours and leave measurable traces reminds us that the galaxy is an interconnected ecosystem where every star contributes to the mixture of materials that in time can form new worlds. From a practical point of view, the tracking of 3I Atlas has strengthened international cooperation between observatories, space agencies, and scientific communities. The coordination between NASA, ESA, the Institute of Astrophysics of the Canary Islands, the European Southern Observatory, and multiple research centers in Asia and America has shown what modern science can achieve when global efforts are united. This model of collaboration will be essential for future missions, especially those designed to intercept or study interstellar objects in real time. The data from 3I Atlas will serve as a reference for planning missions that in the coming decades could approach similar bodies and analyze them directly. The Sun, at the same time, has reaffirmed its role as a natural laboratory. Its behavior during this cycle has allowed for the testing of theoretical models on magnetic reconnection, plasma dynamics, and the influence of the solar wind in interplanetary space. Measurements from the Parker Solar Probe and Solar Orbiter have provided information that helps resolve one of the great mysteries of modern astrophysics: why is the solar corona so much hotter than the surface of the Sun? Every explosion, every flare, every polarity change contributes to understanding the mechanisms that maintain that energetic equilibrium, and at the same time, all that data helps protect human infrastructure from the effects of solar storms. In this scenario, 3I Atlas becomes both a witness and a measuring instrument. Its response to the extreme solar environment acts as a mirror reflecting the Sun's energetic conditions. Every brightness increase, every spectral variation correlates with radiation peaks recorded by the satellites. This symbiotic relationship between a foreign body and our central star demonstrates how cosmic phenomena, although they seem independent, are connected by the same universal physical laws. What happens in the Sun reverberates throughout everything within its gravitational reach. And beyond, from a philosophical and scientific point of view, the passage of 3I Atlas during a solar maximum also invites reflection on the fragility and resilience of life on Earth. The Sun's energy is what allows the biosphere to exist, but that same energy can become dangerous if it overflows. The magnetic fields and atmosphere of our planet act as natural shields, filtering out lethal radiation. Without them, Earth would be as arid as Mars. Observing how an unprotected body directly faces the power of the Sun is a lesson about the cosmic balance that makes our existence possible. Life, as we know it, depends on a very narrow band of stability between the energy we receive and the energy we can withstand. In terms of scientific legacy, 3I Atlas will be remembered as the visitor that arrived at the perfect moment. Its presence coincided with a Sun reaching its point of greatest energy, allowing for an unrepeatable natural experiment. The compiled data will be used for years to refine models on the interaction between stellar radiation and interstellar matter. At the same time, its passage reinforces the idea that the solar system is not a closed space, but part of a constant flow of bodies entering and leaving. This exchange of matter can have profound implications for the understanding of the origin and evolution of planetary systems. The Sun, in contrast, will continue its cycle. After the current peak, it will begin a descending phase in which sunspots and eruptions will gradually diminish, but its energy will not stop. At some point, in about 11 years or so, it will reach another maximum, and astronomers will be ready to observe it with even more precise instruments. Perhaps then another interstellar object will traverse the solar system, offering a new opportunity to compare the radiation of a star in its prime with matter from other worlds. The history of science demonstrates that knowledge advances precisely thanks to these fortuitous coincidences, where time and observation align to reveal something new. Ultimately, the passage of 3I Atlas and the activity of the Sun remind us that the universe is not still. Everything moves, evolves, and changes constantly. The stability we experience on Earth is a temporary exception within a cosmos in perpetual dynamism. And yet, it is in that movement that life finds its place. The energy of the Sun, the particles flowing from its corona, the fragments from other systems crossing our sky, all form part of the same story of transformation and continuity. When the telescopes turn off their sensors and 3I Atlas moves away into the interstellar darkness, what will remain is not just a collection of data, but a lesson about our position in the cosmos. We are observers in a living galaxy, witnesses to processes that began long before humanity existed and that will continue to occur long after. Every ray of light reflected by 3I Atlas, every particle the Sun launched into space, belongs to a cosmic dance that unites the visible with the unknown. The legacy of this encounter between a sun in its maximum splendor and an interstellar traveler will not be measured only in graphs or scientific publications, but in the expansion of human understanding. It reminds us that the universe, far from being a cold void, is a dynamic and coherent organism, where every phenomenon has a purpose within the general equilibrium. 3I Atlas is already moving away, but its passage will be engraved as a brilliant chapter in the history of modern astronomy, the moment when the energy of our star and the matter from another met, illuminating together a universal truth, that everything in the cosmos is connected and that every flash, however brief, leaves an eternal mark in the memory of space.